Welcome students. In this session we will discuss linear functionals. In linear algebra, a linear functional is a linear transformation from a vector space to its field of scalars. In this session we will illustrate the concept of linear functionals through examples. We also describe some results, the interplay between a vector space and its dual space are discussed, the definition of annihilator along with some results is described. We will see that every hyperspace of a finite dimensional vector space is the null space of a linear functional. Linear functional definition 1. Linear functional, let V be a vector space over a field F, a linear transformation T from V into F is called a linear functional. That is, T is a linear functional on V if T is a function from V into F such that T of C into alpha plus beta is equal to C into T of alpha plus T of beta for all vectors alpha and beta belongs to V and all scalars C belongs to F. Example 1. Let V be a vector space over the field F. It can be easily seen that the map 0 from V to F defined by 0 of V equal to 0 for V belongs to V is a linear functional. This linear functional is called the 0 linear functional on the vector space V. Example 2. Verify that the map T from R2 to R defined by T of x y is equal to 2x plus 3y is a linear functional. Solution. That alpha is equal to x1 y1 and beta is equal to x2 y2, then C into alpha plus beta is equal to C into x1 y1 plus x2 y2, which is equal to C into x1 plus x2 C into y1 plus y2, and hence by the definition of T we have T of C into alpha plus beta is equal to 2 into C into x1 plus x2 plus 3 into C into y1 plus y2, which is equal to C into 2 into x1 plus 3 into y1 plus 2 into x2 plus 3 into y2, which is equal to C into T of alpha plus T of beta. Since the choice of alpha and beta are arbitrary elements in R2, the above shows that T of C into alpha plus beta is equal to C into T of alpha plus T of beta for all vectors alpha beta belongs to R2 and all scalars C belongs to R. Hence, the given map T is a linear functional. Example 3. Verify that the map T from R2 to R defined by T of x y z equal to x into y is not a linear functional. Solution. That alpha is equal to x1 y1 and beta is equal to x2 y2, then T of C into alpha plus beta is equal to C into x1 plus x2 into C into y1 plus y2, equation 1, and C into T of alpha plus T of beta is equal to C into T of x1 y1 plus T of x2 y2, which is equal to C into x1 into y1 plus x2 into y2, equation number 2. From equation 1 and 2 in general we have T of C into alpha plus beta not equal to C into T of alpha plus T of beta, hence T is not a linear functional. Example 4. Let F be a field and let A1, A2 etc. A n be scalars in F. Define a function T on the vector space F n by T of x1 etc. x n equal to A1 into x1 plus etc. plus A n into x n, equation 3. It can be seen that T is a linear functional on F n. We now verify that relative to the standard ordered basis B is equal to epsilon 1 etc. epsilon n for F n and the basis 1 for F, the linear functional T is represented by the 1 by n row matrix A 1 etc. A n. Noting that for j is equal to 1 to n, epsilon j is the n tuple with all entries except the jth are 0 and jth is 1. We have A j is equal to T of epsilon j, j equal to 1 etc. n. Hence, matrix of T relative to basis 1 equal to matrix T epsilon 1 1, T epsilon 2 1 etc. T epsilon n 1, which is equal to matrix A 1 etc. A n. Remark. Every linear functional on F n is of the form given in equation 3 for some scalars A 1, A 2 etc. A n. This can be seen as follows, denoting the standard ordered basis for F n by epsilon 1 etc. epsilon n and taking a linear functional T on F n such that A j is equal to T of epsilon j, j equal to 1 to etc. n. Then for any x 1 etc. x n belongs to F n, we have x 1 etc. x n equal to sigma j is equal to 1 to etc. n x j epsilon j. T of x 1 etc. x n is equal to T of sigma over j x j epsilon j, which is equal to sigma over j x j into T of epsilon j, which is equal to sigma j equal to 1 to n A j into x j. Example 5. Let n be a positive integer and F a field. Verify that the trace function is a linear functional on the metric space F n by n. Solution. A belongs to F n by n implies A is an n by n matrix with entries in F. The trace of A is the scalar trace of A equal to A 1 1 plus A 2 2 plus etcetera plus A n n. For A b belongs to F n by n and C belongs to F, we have trace of C into A plus B equal to sigma I equal to 1 etcetera n C into A I plus B I, which is equal to C into sigma I equal to 1 etcetera n A I plus sigma I equal to 1 etcetera n B I, which is equal to C into trace of A plus trace of B. Example 6. Let V be the space of all functions from a field F into itself. Let T be an element of F. It can be verified that LT from V to F defined by LT of F is equal to F of T for F belongs to V is a linear functional on V. One usually describes this by saying that for each T, evaluation at T is a linear functional on the space of functions. Example 7. Let closed interval a b be a closed interval on the real line and let C of a b be the space of continuous real valued functions on closed interval a b. Then it can be verified that L from C a b to R defined by L of g is equal to integral a to b g of t dt for g belongs to C of a b is a linear functional on C of a b. Dual space and dual basis. We recall that if V and W are vector spaces over a field F, then the set of all linear transformations from V into W is a vector space over the field F. As a linear functional is a particular type of linear transformation, the following definition makes sense. Definition 2. Dual space. If V is a vector space over a field F, then the collection of all linear functionals on V forms a vector space and is called the dual space of V. It is the space LVF and is denoted by V star. We now recall a result. Let V be an n dimensional vector space over the field F and let W be an m dimensional vector space over F, then the vector space LVW is finite dimensional and has dimension m into n. Using the above result, if V is finite dimensional, we can obtain a rather explicit description of the dual space V star. Noting that dimension of F equal to 1, we have dimension of V star is equal to dimension of V into dimension of F, which is equal to dimension of V. Theorem 1. Let V be a finite dimensional vector space over the field F and let B is equal to alpha 1 etcetera alpha n be a basis for V. Then there is a unique dual basis B star equal to F 1 etcetera F n for V star such that F I of alpha j equal to delta I j. For each linear functional f on V, we have f equal to sigma I equal to 1 to n f of alpha I into f I, equation 4. And for each vector alpha in V, we have alpha equal to sigma I equal to 1 to etcetera n f I alpha into alpha I, equation 5. Definition. The basis B star equal to f 1 etcetera f n mentioned in theorem 1 is called the dual basis of the basis B. Proof of theorem 1. Let B be a basis for V for each I where I equal to 1 to etcetera n, there is a unique linear functional f I on V such that f I of alpha j equal to delta I j, equation 6. In this way, we obtain from B a set of n distinct linear functionals f 1, f 2 etcetera f n on V. These functionals are also linearly independent. For suppose f equal to sigma I equal to 1 etcetera n C I into f I, equation 7. Then f of alpha I is equal to sigma I equal to 1 etcetera n C I into f I of alpha j, which is equal to sigma I equal to 1 to etcetera n C I into delta I j, which is equal to C j. In particular, if f is the 0 functional, f of alpha j equal to 0 for each j and hence the scalars C j are all 0. Hence, f 1, f 2 etcetera f n are n linearly independent functionals. Also, since we know that V star has dimension n, these n linearly independent functionals constitute a basis. That is, we have shown that there is a unique basis B star equal to set f 1 etcetera f n which is dual to B. If f is a linear functional on V, then f is some linear combination of the f I as in equation 6, and as we observed just after equation 6, the scalar C j must be given by C j equal to f of alpha j. Also, if alpha equal to sigma I equal to 1 etcetera n x I into alpha I is a vector in V, then f j of alpha equal to sigma I equal to 1 to etcetera n x I into f j of alpha I. Since f j is a linear functional which is equal to sigma I equal to 1 to n x I into delta I j by the definition of f j, which is equal to x j. Hence, the unique expression for alpha as a linear combination of the alpha I is alpha equal to sigma I equal to 1 to n f I of alpha into alpha I. Equation 5 says that if B is equal to alpha 1 etcetera alpha n is an ordered basis for V and B star is equal to f 1 etcetera f n is the dual basis, then f I is precisely the function which assigns to each vector alpha in V the ith coordinate functions for B. The formula for when combined with 5 tells us the following: if f is in V star and if we let f of alpha I is equal to a I, then when alpha equal to x 1 into alpha 1 plus etcetera plus x n into alpha n, we have f of alpha is equal to a 1 into x 1 plus etcetera plus a n into x n, equation 8. In other words, if we choose an ordered basis B for V and describe each vector in V by its n tuple of coordinates x 1 etcetera x n relative to B, then every linear functional on V has the form H. This is the natural generalization of example 4, which is the special case V equal to f n and B is equal to epsilon 1 etcetera epsilon n. Example H: R denotes the field of real numbers. Let V be the vector space of all polynomial functions from R into R which have degree less than or equal to 2. Let T 1, T 2 and T 3 be 3 distinct real numbers and let L I p is equal to p of T I for I equal to 1, 2, 3. Then it can be seen that L 1, L 2 and L 3 are linear functionals on V. These functionals are linearly independent. For suppose C 1 into L 1 plus C 2 into L 2 plus C 3 into L 3 equal to 0, equation 9, where 0 is the 0 linear functional. Then applying the 0 linear functional to the particular polynomial functions 1 x x square and using equation 9, we obtain C 1 plus C 2 plus C 3 equal to 0, T 1 into C 1 plus T 2 into C 2 plus T 3 into C 3 equal to 0, T 1 square into C 1 plus T 2 square into C 2 plus T 3 square into C 3 equal to 0. The above is system of 3 equations in 3 unknown C 1, C 2 and C 3. The coefficient matrix 1 1 1 T 1 T 2 T 3 T 1 square T 2 square T 3 square, and this is invertible when T 1 T 2 and T 3 are distinct. Hence, the rank of the coefficient matrix is 3 and hence the given homogeneous system has the unique solution and is the trivial solution, and hence it follows that C 1 equal to C 2 equal to C 3 equal to 0. Hence, L 1, L 2 and L 3 are linearly independent. Since V has dimension 3, the dimension of V star is 3. Hence, the linearly independent functions L 1, L 2 and L 3 form a basis for V star. Now, we search for the basis for V of which L 1, L 2, L 3 is the dual. Such a basis P 1, P 2, P 3 for V must be such that L I of P j equal to delta I j or P j of T I equal to delta I j. Hence, these polynomial functions P 1, P 2 and P 3 are given by P 1 of x equal to x minus T 2 into x minus T 3 by T 1 minus T 2 into T 1 minus T 3. P 2 x is equal to x minus T 1 into x minus T 3 by T 2 minus T 1 into T 2 minus T 3. P 3 of x equal to x minus T 1 into x minus T 2 by T 3 minus T 1 into T 3 minus T 2. Since P 1, P 2, P 3 is a basis for V, using equation 4 we have for each P in V, P equal to P of T 1 into P 1 plus P of T 2 into P 2 plus P of T 3 into P 3. Thus, if C 1, C 2 and C 3 are any real numbers, then there is exactly one polynomial function P over R which has degree at most 2. Result: if f is a non-zero linear functional defined on a finite dimensional vector space V, then dimension of n of f is equal to dimension of V minus 1, where n f is the null space of f. Proof: by rank nullity theorem, rank of f plus dimension of null space of f equal to dimension of V, but the rank of f is 1 because the range of f is a non-zero subspace of the scalar field and hence must be the scalar field. Hence, the above equation yields dimension of n f equal to dimension of V minus 1. Annihilator: in a vector space of dimension n, a subspace of dimension n minus 1 is called a hyperspace. Is a hyperspace the null space of a linear functional? The answer is yes. This can be obtained as a special case of the coming theorem 2. In view of theorem 2, we will describe that each k dimensional subspace of an n dimensional space is the intersection of the null spaces of n minus k linear functionals. Definition 3: if V is a vector space over the field F and S is a subset of V, the annihilator of S is the set S naught of linear functionals F on V such that f of alpha equal to 0 for every alpha in S. That is, annihilator of S equal to set of all f in V star such that f of alpha equal to 0 for every alpha belongs to S. It can be easily seen that annihilator of S is a subspace of V star whether S is a subspace of V or not. Special cases: if S is the set consisting of the 0 vector alone, then annihilator of S equal to V star. If S equal to V, then annihilator of S is the 0 subspace of V star. Theorem 2. Let V be a finite dimensional vector space over the field F and let W be a subspace of V, then dimension of W plus dimension of W naught equal to dimension of V. Proof: let K be the dimension of W and set alpha 1 etc. alpha k a basis for W. Choose vectors alpha k plus 1 etc. alpha n in V such that set alpha 1 etc. alpha n is a basis for V. Let set f 1 etc. f n be the basis for V star which is dual to this basis for V. The claim is that set f k plus 1 etc. f n is a basis for the annihilator W naught. Certainly, f I belongs to W naught for I greater than or equal to k plus 1 because f I of alpha j equal to delta I j and delta I j equal to 0 if I greater than or equal to k plus 1 and j less than or equal to k. From this it follows that for I greater than or equal to k plus 1, f I of alpha equal to 0 whenever alpha is a linear combination of alpha 1 etc. alpha k, the functionals f k plus 1 etc. f n are independent. So, all we must show is that they span annihilator of W. Suppose f is in V star. Now, f equal to sigma I equal to 1 to n f of alpha I into f I. So, that if f is in annihilator of W, we have f of alpha I equal to 0 for I less than or equal to k and f equal to sigma I equal to k plus 1 to n f of alpha I into f of I. We have shown that if dimension of W equal to k and dimension of V equal to n, then dimension of annihilator of W equal to n minus k. Corollary: if W is a k dimensional subspace of an n dimensional vector space V, then W is the intersection of n minus k hyperspaces in V. Proof: in the notation of the proof of the theorem, W is exactly the set of vectors alpha such that f I of alpha equal to 0, I equal to k plus 1 etc. n. Then W equal to intersection I equal to k plus 1 to n, n f I, where n f I is the null space of the linear function f I equal to k plus 1 etc. n. Example 9. Verify that the solution space of a given system of m linear equations in n unknowns x 1, x 2 etc. x n can be regarded as the subspace annihilated by some space of linear functionals. Solution: suppose we try to find the solution space of the following system of linear equations a 1 1 into x 1 plus etc. a 1 n into x n equal to 0 etc. a m 1 into x 1 plus etc. plus a m n into x n equal to 0. Now, let f I is equal to 1 to etc. m be the linear function of f n defined by f I of x 1 etc. x n equal to a I 1 x 1 plus etc. a I n x n. Then finding the solution space of the system of linear equations is equivalent to finding the subspace set of all alpha belongs to f n such that f I of alpha equal to 0, I equal to 1 etc. m, that is we are seeking the subspace annihilated by f 1, f 2 etc. f m. Row reduction of the coefficient matrix provides us with a systematic method of finding this subspace. The n tuple a I 1 etc. a I n gives the coordinates of the linear functional f I relative to the basis which is dual to the standard basis for f n. The row space of the coefficient matrix may thus be regarded as the space of linear functional spanned by f 1, f 2 etc. f m. Hence, the solution space is the subspace annihilated by this space of functionals. Let us summarize this session. In this session, we have seen the definition of linear functional. Some examples and results have been described. The interplay between a vector space and its dual space have been discussed. The definition of annihilator along with some results have been described. We also have shown that every hyperspace of a finite dimensional vector space is the null space of a linear functional. Before we attend the next unit, please try to answer the following questions. Question 1. Let V is equal to R 3 and S is equal to set 1 0 0 1 1 0. Find the annihilator S naught. 2. If W 1 and W 2 are subspaces of a finite dimensional vector spaces, then show that W 1 equal to W 2 if and only if annihilator of W 1 equal to annihilator of W 2. 3. Find the subspace annihilated by the following three linear functions in R 4. f1 of x1, x2, x3, x4 is equal to x1 plus 2x2 plus 2x3 plus x4, f2 of x1, x2, x3, x4 is equal to 2x2 plus x4, f3 of x1, x2, x3, x4 is equal to minus 2 x1 minus 4 x3 plus 3 x4. That is B is equal to alpha 1, alpha 2, alpha 3 be the basis for R3 defined by alpha 1 is equal to 1 0 minus 1, alpha 2 is equal to 1 1 1, alpha 3 is equal to 2 2 0. Find the dual basis of B. See you next time. Till then, goodbye.